Students, welcome back to Differential Equations class. We're going to reach a big milestone today. We're going to wrap up Chapter 4 with Section 4.5, Periodic and Piecewise Continuous Input Functions. This is a great section because we're going to be able to go back and review some of the concepts that we've learned before and compare and contrast them to new information today. And we're also going to get something useful as far as modeling with the spring mass systems. There are a couple of sections that I want to point your attention to remember some important topics that will be useful today. One of those is Section 4.1. So this is from our Section 4.1 notes where we're first learning about Laplace transforms by definition and by table. And in that section, we discussed piecewise defined functions, specifically the unit step function. So the unit step function in general is defined like so. It's 0 for t less than 0 and 1 for t greater than or equal to 0. Looking at the graph, we interpreted the horizontal line at the value of 0 as being off and the horizontal line at 1 as being on. We're going to use this unit step function today as a model to control an external forcing function with a spring mass system that we can turn on or off. If we translate that unit step function, a units to the right, then we can determine the time that we turn that external forcing function on or off. In the translation on the graph that you see here, we have turned it on at a seconds. Also important to our discussion today, not because we're going to be using this skill, but I really want to contrast what we're doing today in Section 4.5 with what we did in Section 4.3. Remember in 4.3, we learned about translation on the s-axis. Now, translation on the s-axis occurs if we have some sort of function of t that we're trying to transform that is multiplied by this additional factor e to the at, which we called eat. So if my function of t that I'm attempting to find the Laplace transform for is multiplied by e to the at, that results on the other side a translation on the s-axis. Remember, we found the Laplace transform of f of t like we normally would by looking it up on the table, and then we evaluated that function at s minus a. So the presence of the factor e to the at on the t side of things creates a translation on the s-axis, and vice versa. If I notice that a function of s that I'm trying to inverse transform is translated a units, then it creates this additional factor in the inverse Laplace transform. So today we're looking at not translation on the s-axis, but translation on the t-axis. So make sure that you pay attention for the difference between those two things because it can get a little bit confusing. One more document that I want to show to you as we progress through our study today. This document is called the Chapter 4 Summary. It is available for you in Blackboard. It's all of the formulas that we've talked about in Chapter 4 in one spot. Now remember, your job is not to memorize these formulas. Your job is to know how to use these because as you've seen, a simple formula can have a complex process associated with it. So specifically today, we will be comparing translation on the s-axis, that's what we learned in Section 4.3, to translation on the t-axis. Okay, so make sure that after today's lesson, you can tell the difference between those two sets of formulas. Translation on the s-axis, we've got that figured out. Today's lesson is translation on the t-axis. Okay, enough explanation. Let's go ahead and get started in the lesson. Let's read the theorem for translation on the t-axis. If the Laplace transform of f of t exists for s greater than c, then the Laplace transform of u of t minus a times f of t minus a equals e to the negative as times big F of s, and the inverse Laplace transform of e to the negative as times big F of s is u of t minus a times f of t minus a for all s greater than c plus a. So let's make some observations about these formulas. First of all, we have the forward direction, where we are transforming the product u of t minus a times f of t minus a. And that gives us e to the negative as times big F of s. And this is simply the reverse of that formula. So I've got a Laplace transform and an inverse Laplace transform, and they are in exact opposite directions of each other, but the details are pretty much the same. The next thing that I want you to notice is the translation on the t-axis. What I mean by translation on the t-axis is the arguments of these two functions are t minus a. We know from college algebra, transformations on the x-axis, this would be a horizontal shift to the right by a units. So that's why we call it a translation on the t-axis. It's simply a transformation of the function. Now, as we execute this, watch the details. These two arguments must be the same. So I'm going to make a note. The arguments must match in order for this formula to work. Sometimes you will have a mismatch between your arguments, and we'll talk about how to correct that specifically with trig identities. The second thing I want you to notice, or maybe the third observation by now, is this function u. That represents our unit step function. So u of t, we studied again in 4.1. Here is u of t minus a. It's simply our unit step function translated to the right. So we're going to be using the unit step function for these Laplace transforms. So if I am attempting to transform an ordinary function of t, which has been shifted by a units, and it is multiplied by the unit step function also shifted, the result on the side of the s-axis is the presence of this e to the negative as term. Okay? Also notice, big F of s is the translation of ordinary little f of t. So the Laplace transform of f of t is big F of s. So here's how I'm going to execute this formula. First of all, I'm going to check a couple of things. I'm going to make sure the arguments match, and I'm going to observe that I've got the unit step function involved in the function that I'm trying to transform. When I transform it, I'm simply going to transform ordinary little f of t. I'm not going to think about t minus a. I'm just observing that the t minus a is there to match the t minus a in the unit step function. So I'm going to find an ordinary transform from the table. That's going to give me big F of s. But because of the shift on the t-axis and the presence of the unit step function, I get this additional exponential factor. Okay, now compare that just to get your wits about you, to get a frame of reference here. If you'll remember, when we learned translation on the s-axis, that occurred when we had this function on the t side of things. If I multiply a function by eat, the result is a translation on the s-axis. Okay, here in this section, we've got a translation on the t-axis, so the result is the presence of this exponential term on the s side of things. Okay, a lot of details, and again, we just have the reverse of that formula right here. So we're going to start with an inverse transform. We'll look at the inverse transform first, and then we will try an ordinary transform. Example 1. Find the inverse Laplace transform of 1 over s minus 4 times e to the negative 2s. So let's make some observations. First of all, I notice this exponential term. Okay, so we're looking at this term right here. The presence, or over here, the presence of this e to the negative 2s predicts a translation on the t-axis. So that's how I'm going to recognize when to use this formula. So the presence of the exponential term e to the negative 2s predicts a translation on the t-axis. Okay, in addition to that, I've got this ordinary function 1 over s minus 4. So looking at our inverse Laplace transform formula, we've recognized the presence of this term, e to the negative as, in this example is e to the negative 2s. And my big f of s then is this right here. 1 over s minus 4 is big F of s. If I inverse transform it, I'm going to get little f of t. So I'm going to do that first, and then I'll worry about the translation on the t-axis. So first note, let me make my notes a little wider here. First note that the inverse Laplace transform of 1 over s minus 4 is, do you know that one by heart yet? Have you done enough of these to accidentally memorize them? If not, that is A-okay. Let's look over here. That is our famous EAT formula, right? So I'm inverse transforming 1 over s minus 4. The result will be e to the 4t. So I'm making the observation that the inverse Laplace transform of 1 over s minus 4 is e to the 4t. Okay, so I did a little mini problem in preparation for the problem we are trying to work. So the inverse Laplace transform of 1 over s minus 4 times e to the negative 2s is going to be u of t minus 2 f of t minus 2. Okay, hold on. Where did all of that come from? Well, I'm looking at this formula right here. I've got my big F of s, that's 1 over s minus 4. I've got the presence of the e to the negative as term, that's e to the negative 2s. So I'm simply following the formula at this point. Now, let's fill in the details. One thing that I want you to observe about this formula is right here we have a negative a, and over here in the argument we still have negative a's. Contrast that for a minute with translation on the s-axis. Notice I had a positive a over here and a negative a over here. Did you see that sign change? Or in the inverse Laplace transform, I have a negative a over here, it becomes a positive a over here. But when we're working on translation on the t-axis, this sign and this sign match. That's just a little subtle difference I wanted to point out. Messes me up sometimes, so I hope that that helps you to pay attention to that detail as well. Okay, that's where I got u of t minus 2, f of t minus 2. Now, u of t minus 2, that's just going to be our unit step function translated to the right by 2 units. So we understand what that is. Now, let's look at little f of t minus 2. Little f of t is this guy right here. This is little f of t. Little f of t is the transform of big F of s. I did that. The presence of the e to the negative 2s term is what causes us to also include this term. So now we can take our little f of t, which is e to the 4t, and we can evaluate it at t minus 2. Make sure you get parentheses around that exponent. Now, expanding this into a piecewise defined function, remember u of t minus a is equal to 0 for t less than a. In our specific case, a is going to be 2. So we're going to say it's 0 for t less than 2, it's 1 for t greater than or equal to 2. So back to our notes, we can say this is equal to 0 for t less than 2, and it's equal to 1 times e to the 4 times t minus 2 for t greater than or equal to 2. Okay? So 0 times the exponential gives us 0. 1 times the exponential gives us just the exponential. So to understand the result of this function, we're going to construct a quick graph. Over here on the right side, we're going to recognize that our horizontal variable is not x, but t, and our vertical variable is the output of our function. Let's just call it, we've got both u and f, so I'm going to say the output is g of t, okay, representing the Laplace transform of the original problem. The translation is right by 2 units, so I'm going to indicate my scales here. And notice we have the function off for everything less than 2. So at 2, we're going to have an open circle or a hole. And then at t equals 2, the value is exponential. So the graph is going to follow the exponential curve from t equals 2 and greater. Now notice if t is equal to 2, the function value there is 1. So this is going to jump up to the value of 1, and then it's going to be an exponential function from then on out. Okay, and that's just a sketch of the exponential function. So what we have here is a piecewise defined function. We can use this, by the way, to model an external forcing function for our spring mass system that is off for a little while, and then it turns on not with a constant function, but with an exponential external forcing function. Okay? All right, lots of little details to watch. Now let's go the other way. We've got this example to do first. No, this is right. We are going the other way. We just found an inverse Laplace transform. Now we're going to find a forward direction Laplace transform. But notice we're transforming a piecewise defined function. Observe the nature of this piecewise defined function. It's equal to 3 cosine of t for 0 less than or equal to t less than pi. So we can say that it is on for about 3 seconds, right? Approximately 3.14. Then at pi, or 3.14 approximately, the function is turned off. So what we want to do is sketch a quick graph of this function, and then we're going to express this in terms of the unit step function. So looking at our graph here on the right, we're going to say the horizontal variable is t. The vertical value here, we're representing g of t, and I'll use a scale of pi over 2. So this is pi over 2, pi, 3 pi over 2, 2 pi, so on and so forth. And notice our function is going to follow 3 cosine of t between 0 and pi. That's an ordinary cosine wave with an amplitude of 3. So thinking about our cosine wave, it starts up at the amplitude, it crosses at pi over 2, reaches its lower amplitude at negative pi, and if we continued past here, you'd be able to see the rest of the cosine wave, right? But we just want the cosine wave for t between 0 and pi. As soon as we get to pi units, the function value is 0. Now, notice the pattern of this piecewise defined function. I have activity first and then a flat line second. That's the opposite of our unit step function, right? We have a flat line off first and then it jumps up to on second. So here we might say this is on with a cosine wave and then it turns off. So I've kind of got a mismatch in the coordination between the pattern of off, on, and on, off. So what I want to do is rewrite this function in terms of the unit step function. I'm going to manipulate the unit step function to match this pattern. Now, because we have this piecewise defined function, our goal is to express it something like this so that we can find the Laplace transform. So we want to multiply it by a properly transformed unit step function. So I'm going to take you through the different transformations that you want to think about as you rewrite this original function g of t in terms of the unit step function. First thing I want you to think about is u of t minus pi. So if we look at u of t minus pi, I'm just going to put pi right here, and we'll say on is right here. So ordinary u of t minus pi is our step function, which is off until we get to pi, and then on when we get to pi, okay? Again, notice the mismatch in the pattern. This one is 0 first and then 1 second. And the problem we're trying to model is the opposite. It's on first and then it's off. So we want to flip that around. So what I'm going to do is reflect this function across the t-axis. And we're just thinking about algebraic transformations here. I'm going to reflect this function across the t-axis by multiplying it by a negative. So let's invert our function. Think about the mirror image of that function on the other side of our horizontal axis. It would look, whoops, backtrack, sorry, got ahead of myself. The off part is going to stay right on top of itself. No change. If I'm reflecting that point across the t-axis, it stays right there. But when I reflect this part across the t-axis, it lands like so. So now the pattern's a little better. You've got your left side higher than your right side, but it's still 0 and -1. We need it to be 1 and 0. So I'm going to do one more transformation. Here's the function we just graphed, reflected across the t-axis. If we add 1 to a function, remember algebraically, that's a vertical transformation up 1 unit. So I'm going to take my function and I'm going to shift it up the y-axis, or in this case our u-axis, 1 unit. So taking that flat line that's originally at 0 and moving it up 1 unit, it ends right here. And then taking this branch and moving it up 1 unit, we end up right here. So now look at the pattern. Just by applying these algebraic transformations, this has a value of 1, so we're going to call that on. This has a value of 0, so we're going to call that off. So now the patterns match, right? The original function that we're trying to transform, g of t, is on. Happens to be a cosine wave, but we'll say it's on. And then at pi seconds, it has a flat line value of 0. The unit step function that we ended up with is on until pi seconds, and then it's off beyond that. So now all I have to do to express my original function g of t in terms of this unit step function is multiply those two together, okay? We have a little bit of extra room at the top of the next page, so we'll carry that out on the next page. We can say, therefore, the original function g of t, which I'm attempting to find the Laplace transform for, is now expressed as 3 cosine of t times 1 minus u of t minus pi. Okay, so that causes this first branch, when I multiply it by 3 cosine of t, to match the original function. And then they're both 0 from pi units onward. And we're only going to be modeling this for the least value t equals 0. Okay, now we're ready to transform. Before we transform, let's distribute our cosine. We have 3 cosine of t times 1 minus 3 cosine of t times u of t minus pi. The next step is to transform. We're going to be able to handle these two terms individually. However, because we have the presence of that unit step function in the second term, remember, we have to have these two arguments match. So the arguments must match. So I want this to look like f of t minus pi, u of t minus pi, because that's what we have in our original formula. So let's just use a trig identity to execute that. We would prefer that it said cosine of t minus pi. So let's find the relationship between cosine of t and cosine of t minus pi. Well, cosine of a difference has an identity associated with it. That's cosine of t, cosine of pi. What do you think, plus or minus? It's plus sine of t, sine of pi. Hope you got that right. Now, cosine of pi has a value of -1, and sine of pi has a value of 0. So we can simplify this to negative cosine of t, okay? Now, negative cosine of t is equal to cosine of t minus pi. Notice here, if I ignore the 3, I've got negative cosine of t. I'm going to replace that with positive cosine of t minus pi. So I can rewrite this, 3 cosine of t plus 3 cosine of t minus pi u of t minus pi. Okay, so I'm just prepping this function for Laplace transform. Now our two arguments match, and we have the presence of the unit step function, which means we can transform it. Also, please notice that sign change. We started out with a negative here, and now it's positive because negative cosine of t is equal to positive cosine of t minus pi. So just little details. All right, our function is finally ready for Laplace transform. Therefore, the Laplace transform of our original function from the problem is now going to be calculated as the Laplace transform of this expression. So we will apply the Laplace transform to each term individually. We can write this as 3 times the Laplace transform of cosine of t plus 3 times the Laplace transform. Notice we have f of t minus pi, u of t minus pi. That's translation on the t-axis. That's our new formula. Now let's pop over and find the Laplace transform of cosine of t. If you don't have it memorized already, cosine of 1t transforms to s over s squared plus 1. So this becomes 3 times s over s squared plus 1. Okay? Now, let's figure out what to do with the translation on the t-axis. I observe translation on the t-axis and the presence of the unit step function. Therefore, according to our formula, I'm going to come to this one just because it's a little bit cleaner. We've got these two arguments matching. We've got the presence of the unit step function. So, the Laplace transform, it's got to have this term, e to the negative as, and big F of s is the transform of little f of t, ignoring that translation. Now, little f of t, cosine of t, we just did that over here, right? So I need to multiply that function by e to the negative pi s. E to the negative pi s, that's the e to the negative as from the formula. And then look, ordinary transform of cosine of t. What's the point of that minus pi? Just to match this argument, to match the formula. But all I'm doing there is transforming that cosine of t minus pi function as if it were cosine of t. Okay, we're done. All we have to do is simplify. Both of these fractions have the same denominator, so I'm going to go ahead and combine them over one denominator, and the numerator is 3s plus 3e to the negative pi s, which might be better if we factor out the 3s. Call it 1 plus e to the negative pi s over s squared plus 1. So what does this tell me? Why is this useful? Well, if I go back to this function, the original function that we were transforming, it's a broken function. It's a piecewise defined function. I can use this as an external forcing function in a spring mass system where I turn the external forcing function on and off. So in our next example, we're going to see how the Laplace transform is so useful. Because the Laplace transform of the piecewise defined function exists, makes it really easy to solve the differential equation. So in the next problem, we're going to use this function that we just transformed in a spring mass system. Example 3. Suppose a mass weighing 32 pounds, which is one slug, is attached to the free end of a long light spring that is stretched 1 foot by a force of 1 pound. This makes it really easy. The spring constant there is K equals 1 pound. The mass is initially at rest in its equilibrium position. Beginning at t equals 0 seconds, a force of g of t equals 3 cosine of t is applied to the mass. But at time t equals pi seconds, the force is turned off abruptly discontinued and the mass is allowed to continue in motion unimpeded. Find the resulting position of the mass x of t. So I've got a base attached to a spring stretched by a mass. At t equals 0 seconds, I'm going to begin oscillating the base, and it's going to go up and down according to a cosine wave. So it's going to move down, it's going to compress the spring, and then it's going to move up, and it's going to stretch the spring. Okay, so my base is moving up and down, which is affecting the position of this mass, which is going to be modeled by x of t. So we want to figure out what's the position of the mass based on its mass and its spring constant, with the addition of the fact that I'm moving the base up and down with this harmonic oscillator. That is, it's periodic. It's moving up and down according to a cosine wave. But I'm only going to do that for about 3.14 seconds. And then I'm going to turn that off, and the base will be rigid, but the mass is going to continue to oscillate with the lasting effects of that external forcing function. Okay, so sounds like a really hard problem. Laplace transform makes it really easy. Okay, I'm going to need this space to work the problem, so I'm going to move my diagrams out of the way here. You can also use the back side of your notes if you need extra space, or you guys have learned by now, you got to write really tiny, right? There's a lot of work that we try to fit into one little tiny space. Okay, trying to get all these dots to go away. So if you'll recall, the differential equation for our spring mass system is mx double prime plus cx prime plus kx equals f of t. M is the mass. C has to do with resistance to motion. In this case, there is no dash pot or any kind of damping forces present. So in this case, C is equal to 0. K is the spring constant, and f of t is the external forcing function. We can fill in the details of our particular problem. Since m is equal to 1, c is equal to 0, k is equal to 1, we end up with x double prime plus x equal to, let's call this g of t, where g of t, remember it was 3 cosine of t for t 0 to pi, and then at pi, we turned it off. Okay, this function is what we just transformed. So now we're using this as our external harmonic oscillator, or our external forcing function. Okay, now we're going to solve this with Laplace transforms. Let's go ahead and complete our model, though. There's a couple of important pieces of information we need to pick up here. The mass is initially at rest in its equilibrium position. From that, I'm going to derive the initial conditions. It's initially at rest, so its initial position is, it's initially at equilibrium, so its initial position is 0, and it's initially at rest. That means its initial velocity is 0. So we've got our initial value problem here. Kind of tough to deal with if you've got this piecewise defined function. If you want to break it up into 2 different differential equations and solve it, you could. Or you could handle it all in one step with the Laplace transform. So we are going to transform this function. So we're going to find the Laplace transform of x double prime plus the Laplace transform of x equal to the Laplace transform of g of t, which we have already conveniently evaluated. Now, think about our formulas. Don't forget, all of your formulas are here on this one page. So when you do get ready to do your homework or take a test, this is really useful. We are looking at transforming a second derivative. So recall, Laplace transform of x double prime becomes s squared big X of s minus s little x of 0 minus little x prime of 0. The Laplace transform of x is big X, And the Laplace transform of our piecewise defined external forcing function, we just found that up here. So I'm going to go ahead and write that in right here. This is 3s times 1 plus e to the negative pi s over s squared plus 1. Okay, now we're using my favorite initial conditions. They're all going to zero out. X of 0 is 0, so I'm going to lose that term. X prime of 0 is 0, so I will lose that term as well. Let's go ahead and solve this for x. So factoring out big X on the left, we get s squared plus 1. No change over here on the right side. And then divide both sides by s squared plus 1. So that now we have on the bottom s squared plus 1 quantity squared. So we have solved the differential equation for big X. This is big X of s, which represents the Laplace transform of the actual solution little x of t. So in order to finish our problem, we need to find little x of t using an inverse transform. So our next goal is to inverse transform the problem. Little x of t is the inverse Laplace transform of big X of s. Okay, so we need to find the inverse Laplace transform of 3s times 1 plus e to the negative pi s over s squared plus 1 squared. Now, in order to make this convenient, let's break this up into two terms. I'm going to distribute the 3s in the numerator on the top and then put each of those two terms in the numerator over that same denominator. So it becomes inverse Laplace transform of 3s over s squared plus 1 squared plus 3s e to the negative pi s over s squared plus 1 squared. Now that we have two terms, we can inverse Laplace transform each term individually. Now, the first term is going to be pretty straightforward, but I'm hoping that you look at this e to the negative pi s and little alarm bells are going off in your mind. The presence of e to the negative pi s indicates a translation on the t-axis. Okay, let me put those together one more time just to make this association. I hope these associations help you to learn the formulas. But if you have the presence of e on the t side of things, then it's going to create a translation on the s side of things. Or if you have the presence of e on the s side of things, it creates a translation on the t side of things. So watch for that exponential term. Okay, let's go ahead and split up our transforms. We could write this as 3 times the inverse Laplace transform of s over s squared plus 1 squared. That's going to be an ordinary lookup on the table. And this one, 3 times the inverse Laplace transform of s e to the negative pi s, that's going to create a translation over s squared plus 1 squared. So the next step is to find the inverse Laplace transform of s over s squared plus 1 squared using our table of Laplace transforms. So we have an s in the numerator, and notice we have a squared denominator. So this is the formula that I'm going to be using. The inverse Laplace transform of s over s squared plus 1 is t over 2 sine of t. Notice in our specific problem, k is equal to 1. So we're going to get t over 2 sine of t. So we have 3 times t over 2 sine of t. Now, this one's going to be a little bit different because we've got that e to the negative pi s. So what we're going to do is recognize the ordinary inverse Laplace transform as if the e is not there, which by the way we just did over here. And then we're going to evaluate it at t minus pi. Let's look at the formula to make sure you understand what's going on. So I have an ordinary function of s over s squared plus 1 squared. I'm going to inverse transform that to get little f. And then I'm going to evaluate that little f at t minus a or t minus pi and then multiply it by the unit step function. Okay? So this gives us t over 2 is the first term, but we're going to evaluate it t minus pi over 2 times sine of not t, but t minus pi, and then we're going to tack the unit step function there on the end. Okay? Now, let's clean it up. This is 3/2 times t sine of t plus t minus 2 sine of t minus pi u of t minus pi. Now remember, this is giving me the position of that oscillating mass at any time t. Now we might want to break down that unit step function so we have an understanding of how is this affecting that mass. The external forcing function is turned on for about 3 seconds and then it turns off. Now remember, u of t minus pi, let me just make a note over here. I'll come back up here. Just a reminder, u of t minus pi, first it's equal to 0 between 0 and pi. And then it's equal to 1 for t greater than or equal to pi. Okay? I'm going to use that to simplify our function a little bit. So refining our solution, x of t, we can say, oh, and let's do one more thing. Let's use our handy-dandy trig identities to evaluate sine of t minus pi. So sine of t minus pi is sine of t cosine of pi. Quick pop quiz for trig. Is it plus or minus? I hope you said minus. Cosine of t sine of pi. Cosine of pi is -1 and sine of pi is 0. So sine of t minus pi is equal to negative sine of t. Okay, so I can use that to simplify this term. Now, let's get back to refining our solution. X of t, the first thing I'm going to do is apply this trig identity, is 3/2 t sine of t plus t minus 2. Now, sine of t minus pi is equal to negative sine of t. So I'm going to simplify that, and then we can work on this unit step function. Okay, let's break this into a piecewise defined function. First of all, when t is between 0 and pi, the unit step function has a value of 0, which means my function simplifies to 3/2 t sine of t. This is for 0 less than or equal to t less than pi. Okay? Now, when t is equal to pi and greater, this function has a value of 1. So our unit step function becomes 3/2 times t sine of t minus, that should say t minus pi, shouldn't it? Get that fixed. T minus pi sine of t times 1. Okay, let's clean that up a little bit. First line is good to go. Now the second line, we have t sine t minus t sine t plus pi sine t. So we end up with 3 pi over 2 sine of t after we simplify. So this is a piecewise defined function which describes the motion of the mass. Notice for the first 3 seconds, the amplitude of our mass above and below equilibrium is increasing linearly. If we left that external forcing function on, the amplitude would continue increasing as t increases and eventually destroy the system, right? If the amplitude of oscillation keeps getting bigger and bigger and bigger, the mass is going to oscillate high enough to destroy that base. However, we turn the function off at pi, and then we have a steady state solution. We simply have a harmonic oscillator that doesn't have any sort of damping forces, so it's permanent, and we end up with something that looks like this. Now the graph on this one is really not that exciting. If we look at the value of the function at t equals 0, because sine of 0 is 0, it starts out with a value of 0. When we look at the value of this first function plugging in pi over 2, we end up with sine of pi over 2, which is 1, and we get an amplitude of 3 pi over 2. So it goes up to 3 pi over 2 for the next spot. At pi, sine of pi is 0, so it's back down to 0. Okay, so that first part does something like this. Then, when we turn the external forcing function off, it's going to follow an ordinary sine wave for indefinitely, right? So, in this case, when t is equal to pi, sine is 0, so it's going to match up on this term. And then the sine wave is just going to continue oscillating indefinitely. Okay, so what's interesting about this first part, if we did not turn that external forcing function off, then what we're going to see is the amplitude would continue increasing bigger and bigger each time until the system is destroyed. But because we turned off that external forcing function after about 3 seconds, we end up with this nice steady state oscillation with no damping. That means it continues on forever. So the Laplace transform is useful in this particular model because we had a piecewise defined external forcing function, which we can treat as a whole. We don't have to break it into 2 different functions. We can transform it and get a single function of s, and then inverse transform it and get our original piecewise defined function as the solution. So Laplace transforms are really useful when you have piecewise defined functions in your models. Okay, we've got one more topic to discuss, and we will complete Chapter 4. This is a big milestone in your study of elementary differential equations, Laplace transforms. It's quite a skill to know, so good job making it this far. Last thing we're going to talk about is transforms of not piecewise defined functions, but periodic functions. So what do I mean by a periodic function? An example of a periodic function might be a sine wave, a cosine wave, a tangent curve, something that has a repeating pattern indefinitely over a specific period. Here's the mathematical definition of a periodic function. If a periodic function f has a period p greater than 0, then f of t plus p equals f of t. Think about taking your sine wave and translating it to the right by 2 pi units. You're going to land right on top of the next fundamental cycle. So if we have a periodic function involved in our differential equation, it's fairly simple to find the Laplace transform for. Here's the theorem. Let f of t be periodic with period p and piecewise continuous for all t greater than or equal to 0. Then the Laplace transform exists. That's quite a statement. The Laplace transform of a periodic function exists for all s greater than c and is given by big F of s equals 1 over 1 minus e to the negative ps times the integral from 0 to not infinity, but whatever the period of the function is, e to the negative st f of t dt. So you see this from the definition of the Laplace transform, but again, the upper limit is not infinity. It is simply what the period is. So because this function repeats indefinitely, then we can transform it very simply. So in example 4, we're going to find the Laplace transform of the square wave function. The square wave function is graphed over here to the right. So notice it has a value of 1 for a little while, and then 0, and then 1, and then 0. So this is a repeating function. We see the first two fundamental cycles. Here's the first fundamental cycle, here's the second fundamental cycle. So I could observe that the period of this function is 2 because that pattern repeats every 2 units. This could be used to model an external forcing function that is on and then off, and then on and then off. When my kids were little, they were fascinated by the light switches, and they would turn them on and off and on and off. It drove me nuts, but you could certainly model that with the square wave function. So our job is to find the Laplace transform of this square wave function. Now let's get a little bit of details about this function. Over the period, which we decided is 2, we could say that the value of the function is 1 for t between 0 and 1, and 0 for t between 1 and 2. And we could make the observation, if I translate this to the right by 2 units, I end up with f of t. Okay? So it's definitely periodic. Since it's periodic, I can find the Laplace transform using this new formula. So let's get it done. The Laplace transform of f of t is equal to 1 over 1 minus e to the negative. Remember, the period for this one was 2, so we're going to have negative 2s times the integral from 0 not to infinity, but to the value of the period, which is 2, e to the negative st f of t dt. Now, the value of f is different depending on the value of t. So let's go ahead and break this up into 2 integrals. First, we're going to integrate from 0 to 1 and then 1 to 2. So this becomes the integral from 0 to 1 of e to the negative st times the value of f between 0 and 1, which is 1. Then we're going to integrate from 1 to 2, e to the negative st times f. The value of f between 1 and 2 is 0. And I don't know about you, but I'm thinking that's going to be an easy integral, right? That second integral completely goes away. And so we've whittled this down to evaluating just one integral. So we have 1 over 1 minus e to the negative 2s. Let's go ahead and integrate with respect to t. So we have e to the negative st over negative s. Remember, we're integrating with respect to t, so s is constant with respect to t. Also, because we are integrating with respect to t, we're going to plug 1 in for t, not s. So we have e to the negative s times 1 over negative s minus e to the negative s times 0 over negative s. Let's continue simplifying. We could call this, notice we've got a common denominator here of negative s. So we could call this e to the negative s minus e to the 0th, which is 1. Now, let's reverse the terms in the numerator and cancel the negative in the denominator. You can think of this like I'm factoring a negative 1 out of the top and canceling that negative with the denominator. Okay, now it's tempting to stop there, but there's kind of a cool pattern we can recognize on this one. In this first denominator, it may not look like it, but we actually have the difference of 2 squares there. So we could factor this as 1 plus e to the negative s times 1 minus e to the negative s. Right? That's just the factorization of the difference of 2 squares. which was useful because we can cancel one of those factors. And we've got our Laplace transform. So we have 1 over s times 1 plus e to the negative s. So what does this tell us? If we use an external forcing function on our spring mass system that is periodic, like the square wave, on, off, and we could have some sort of variation. We could have a part of a cosine wave and then turn it off, part of a cosine wave, turn it off. If we have a periodic function, even piecewise periodic, then we can transform it into a single function of s and solve a differential equation that involves that periodic or piecewise defined function. So Laplace transforms are really, really useful in that respect. Now, keep in mind, one more time, we are finished with our Chapter 4 study of Laplace transforms. You can print this formula sheet from Blackboard so you've got all of your formulas in one spot. You do not have to memorize these formulas. You just have to know how to execute them. They are short little one-line formulas, but as you've learned, they can be pretty complicated in the process. We did not talk about the Dirac delta function. That is in the next section. If you're interested in learning about that, it is useful in modeling the spring mass system, where instead of having some sort of function that oscillates the base, I may come with a hammer and do one massive blow to that mass, one pounding of the hammer, and see how that affects the mass. So if you're interested in reading about that, you certainly can in the next section, but you will not be responsible for that on the test. Okay, I hope you've enjoyed your study of Laplace transforms. I wish you the best of luck on your homework and the best of luck on your soon upcoming Chapter 4 exam.